In this video, we're going to talk more about how to solve linear programming problems. And besides using the LP solvers, there are other methods we could use to solve linear programming. We could use the graphical method, and we are going to grab one quick sample of what the graphical method looks like. So let's say we have two variables x and y, and our objective function, we want to maximize x plus y such that y minus x is less than or equals 1, x plus 6y less than or equals 15, 4x minus y less than or equals 10, where x and y are both greater than or equals 0. To solve this graphically, we want to first draw the corresponding graphs and then visualize its corresponding regions. So to do that, let's quickly draw a plane. This is a plane, y-axis, x-axis. So let's pick the first inequality, y minus x less than or equals 1. So what we do is we replace y and x with 0 two different times, one at each time, to kind of gauge the axis through which the line passes through. So if we replace, when x is 0, y is 1, right? So at this point, x is 0, y, let's say this is 1, so y is 1, is going to pass through here. And when y is 0, what would x be? When y is 0, x would be minus 1, right? When y is 0, x will be minus 1. So when this is x as minus 1, let's say this point is minus, no, let's say this point is minus 1, right? So when y is 0, so this graph would pass, this is not very accurate, but it's going to pass through this line. So we have this inequality, let's call it inequality A, this is A, it's going to pass through this line. Okay, let's consider the second one. We have x plus 6y less than or equals 15. So if y is 0, x would be 15. So where y is 0, x is 15. So let's say this is x15, right? And where x is 0, y would be 15 divided by 6. So when you draw that, you should have something that looks more like this. More like this. Maybe, let's see, I want to use another color. Let's say more like this. And when you do the same for this, B, when you do the same for this, you would have something that looks more like this, right? So now you have, let's use another color. You have something that looks more like this, right? So now you have the region of interest. So we're going to call this place, we'll call this a region of interest. So to maximize this objective function, we want to find the inner feasibility region, which is also the region of interest. We want to travel along the distance 1 by 1, and that's because the coefficient of x is 1 and the coefficient of y is 1. So we want to find at what point in this region of interest maximizes x plus 1, x plus y, maximizes our objective function. Now, because our objective function, each of these two variables, x and y, has a coefficient of 1, we can start from a point 1, 1. So let's draw that. Let's say this is 1, 1. This graph is not very accurate, but let's say this is the point 1, 1. So we want to travel along this direction of 1, 1 to find the maximum corner, or the last point where a line perpendicular to it touches the quadrant. So if we want to do that, let's say this is, I think this looks straight. So if we want to draw a line perpendicular to this, we could go this way. This is perpendicular. You draw a line perpendicular to this. you keep extending this one line, right? The line from the point where x is 1 and y is 1, you keep extending it. And as you extend it at each point, you draw a line perpendicular. So this is 1 by 1, you draw a line perpendicular. We extend it to 2, 2, you draw a line perpendicular. That way, 3, 3, you draw a line perpendicular. The point that maximizes your objective function is the last point where that perpendicular line touches the quadrant or area of interest. And in this case, we should, this is area of interest. So we should have a line that touches it at this point. So this point right here becomes max x plus y. Supposing our objective function was x plus 2y, it means this first line wouldn't be at 1, at the coordinates 1, 1. It's going to be at the coordinates. Supposing our objective function was max x plus 2y, graphically, this line would be at 1, at the coordinates 1, 2. Accordingly, if our objective function was, let's say, maximize 3x minus 2y, it means that this line would be at the coordinates 3 minus 2. So that's how we go about it graphically. So, and supposing we had 3 variables instead of this flat graph that we have, we want to look for an intersection of the 3 planes. There are other methods of solving LP. We have the simplex method. We call it simplex method. We have the simplex method, which is computationally expensive, by the way. It goes 2 raised to power O and M. And we also have the interior or ellipsoid method. And the complexity of the ellipsoid or the interior method is polynomial. So, but we won't be talking about these other 2 methods today. One thing we note here is that we are looking for integer solutions instead of a real solution. And sometimes there is no guarantee that the corner solution point is an integer. So in this case, our solution should be the extreme integer points on that solution line for maximizing your objective function. So we can as well scan all involved points on the line in the feasibility region to find out which ones are extreme, or in other words, which one maximizes our objective function. We are going to end this video for now. In the next video, we would continue by using LP to model other kinds of problem. I'll see you on the next one.